to enter Chapter 7. The goal will be to, Chapter 7 is probably going to be 2 days long. We will roll right into Chapter 8. I doubt we're going to finish Chapter 8 before we do the test next Monday, but we'll get where we. Okay, so wherever we get to on Fridays, where the exam will be. Okay, so the topic of Chapter 7 is the thing that we've been doing in the lab, and that's doing titrations. We're taking a reagent, reacting it with an unknown, and from that we're establishing the concentration of that unknown in some form. So we're going to talk about some titration calculations first. So that's actually what we're doing. I've got the order on the outline out of whack. We're going to just look at some examples like that. Then we're going to talk about precipitation titrations, which is something we don't do here at Southeastern as much anymore. We used to do it a lot. The problem with precipitation titration is they almost always involve a heavy metal, and there's become disposal costs associated with that are cost prohibitive. The most common way that we used to do it is silver. And since my silver sold for just on the common market for jewelry grade silver sold for about $12 an ounce when I became a faculty member here. It's considerably higher than that now if you follow precious metal prices. So went up a factor of 50. So it's become if you invested in silver as an infant, you did good. So you probably didn't do that. We're going to talk about how we do titration curves with precipitations, deal with mixtures, and how we can detect endpoints. Now, the thing that's missing out of this is acid bases. So that's where we're going to roll into following this up. Okay. So if we look at titrations, I talked about this in the video. This is an example of a protein that's being titrated with the amino acid or the protein ribonuclease. It's 124 amino acids. There are a total of 36 that have ionizable side groups. That means there are 36 protons that can be titrated off of this protein during the course of the titration. This titration curve, which is plot of a pH versus the protons accepted, are hydroxides that have been added. Every one of those is represented by a dot in this. And that's about as complicated a system that you would ever imagine doing. Now, I tell you, the only practical purpose of this creating such a curve is seeing where the protein is electroneutral, where it doesn't move in an electric field. It's called the PI value. Okay, and that certainly has an application in the separation of proteins. You talk about that in biochemistry. But this concept that you can take and visually look at a plot of pH, something we can measure, versus the way we typically measure it is the volume of a titrant. We can monitor the course of a titration to find out what the course of the titration is. And I talked a little bit about your replacement in the video. Auto titrators are something that are here today and they're here to stay. And just some number values. If you hire an analyst in the lab to do titration types analysis, reality is that that person's going to cost on average between $75,000 and $100,000 a year. Because the benefits package, when you're an employer, your benefits package runs 50% of the person's salary. Time you pay their insurance, you pay their retirement, you pay their Social Security and everything else. So you get a person that you hire from anywhere from $40,000 to $60,000 a year, national average, and you put them to do titration types analysis. This is absolutely your replacement, because the auto titrator like this costs about that one as pictured costs in the neighborhood of $14,000. It doesn't take lunch breaks, it doesn't make mistakes, and it will outdo a person by a factor of 10 to 1 in terms of its throughput per day. It's just the reality. The first group of auto titrators that we set up, the company I used to work for, Monsanto, glyphosate was our #1 product, Roundup. So we made Roundup. We sold $6 billion of Roundup a year. And that was in the 1990s. We had a lab that had over 60 people in it that did titrations, glyphosates and acid. We titrated every lot of glyphosate that went out of the plant. We had to. We took that lab of 60 people and did some automation with some robots that actually weighed the samples out. The robots would ship the samples over to auto titrators, and we put out a series of 10 auto titrators, and 60 people got reduced to 3 in 6 months with automation. And this has happened in hospital labs and everywhere else. When I came here in 95 and I started taking students to tours of TMC, the lab at TMC, we did that for 5 or 6 years. TMC had med techs, and in the med tech lab, they were running 20 people per shift. And they were running, except for the midnight or the late night shift, it was running about 10. Surgery had their own lab, and they were monitoring every type of thing everything that you would do on a chem report. They had an analyst, a trained biologist chemist, sitting there doing those analysis. Today, there's one big machine that does 300 different tests, and all they have are phlebotomists that are trained to draw blood. The doctor says on the floor what he wants, so he gets it on his tablet. It sends it to a barcode printer, which prints the labels, which they can automatically stick to the test tube, and it drops down. Somebody puts rubber bands on it and gives the phlebotomist picks up the orders. They fill the number tubes. They shake it up as they're walking. They drop it in the machine, and it automatically spits the numbers back out on the floor to the nursing staff and the doctor. I mean, it's took a TMC had a director of MedTech, which was a master's level person. Every shift manager was a master's level person. Everybody knew how to do all the tests. They had 50 to 60 different MedTech analysts that ran that program. And the last time we tried to do a tour there, the one person in the lab, all they were responsible was to refill the reagent machine and had absolutely no idea how. Its technology has changed our jobs. Certainly in my career, it'll be changed forevermore. We analyze for more things than we ever imagined, with greater precision, greater accuracy, and at lower concentrations. But this guy is fundamentally, you have a reagent in here of known concentration. This is called a syringe pump. It draws a volume into here, and that slowly pushes it back out where it's going into, this is can't see it very clearly, but some type of a meter. It could be a pH meter. It could be an ion select electrode. It could be a number of things, but it monitors the course of the titration. It does it over and over with phenomenal precision. So in titrations, we want to take our standardized reagent. We want to find out exactly how much analyte's been consumed the same way that you've been doing in lab. You take your reagent of known volume, relate that to the concentration. With the stoichiometry, you can find the moles of the analyte that have been reacted, and from that we can determine concentration. Sometimes when we do titrations, I did this on the video, we do non-traditional things. So this example was what the authors chose to look at the sulfate that was measured with a precipitation reaction. So they participated with barium. So you can take a barium chloride and you can precipitate out the sulfate. You can monitor the course of this titration by looking at the signal from the barium, how much barium's in solution, to see how much have you completed this titration to find out is all the sulfate gone. So what makes this a little bit more challenging is we didn't go to Mars, bring samples back. We had to do the chemistry on the surface of Mars. So whenever you do a analysis like this, the Phoenix rover had 20 different instrument packs on. So when NASA wants you to develop an instrument pack, I was actually contacted to try to develop an instrument pack for amino acid analysis, and was asked to put a proposal in for that. In the late 1990s, I wrote several of the reviews for amino acid analysis. They don't realize we don't, not a graduate program at that time. But the entire analysis, number one, you've got to push this thing, plan it away. You've got a space limitation. So their limitation then was 1.3 kilograms for amino acid analyzer. And it could be no more than 10 by 10 by 4 centimeters. That's the size of the instrument pack that could go in this probe. And then there were power restrictions. It could pull no more than like 100 watts of power to do an analysis, because they're getting all the power coming off of the solar panels that are on the instrument. It was really a technology demanding idea, but they developed these things. Here's just the analysis. It's a slow reaction, but they get a scoop of soil, so you can see the scooper. Gets a scoop of soil, puts it onto the soil. It seals it, shakes it into it. It adds a calibration solution with chloride to get the electrode, make sure it's working right. Then it adds the barium to it, begins to enter the cell, and it continues to enter the barium chloride as they're monitoring that until they get this big jump, and that tells them that's the end of it. Then they can relate this total amount of time, which represents, in their case, the moles of barium that's added. From that, the moles of sulfate. I actually got to review this proposal when I was in graduate school. That's to see something go from a paper concept to being in place on another plant is pretty cool. But I'll tell you, this plant from planning stage, they started planning for this. I looked at this proposal in 1992. Okay, and it didn't shoot off until 2004. It takes a lot of times you do something like this, 10 plus years in the planning phase. You go through endless number of tests before. Cost $250 million to put that program to Mars. It's an expensive endeavor. All right, things that we use: titrant, equivalence point, endpoint. Those are things that we've been using already. One that's a new one that applies to the lab that we're doing today. And the thing that I'll warn you on this lab, this is the most complicated set of calculations you'll do in lab this year. We're doing what's called a back titration. In back titrations, you add an excess of reagent initially, which reacts with completely all of the moles of the analyte, and then you add something else to find out how much excess reagent's made. The reagent that we're using is triiodide, which reacts with oxygen in the air very rapidly, so you can't make it up in advance and standardize it unless you're working in an inert environment. Otherwise, the oxygen in the air, if you let the beaker of this stuff expose to the air, triiodide, if anybody that's old school had their gave blood and they put iodide on your arm to sterilize it, it has that yellow color to it that fades with time. Okay, if you remember what that looks like, if you saw anybody do it, the yellow color was there and it disappears with time. It's because it's reacting to the oxygen in the air, right? And it disappears. So that's the type of analysis. We'll go over that when we do pre-lab. The other thing is to make sure you understand is the equivalence point is some theoretical entity. We don't know exactly where that is. We estimate that, and we say the equivalence points when we've consumed all the moles of the analyte. We can't see a solution at a molecular level to know when all of it's actually gone. All we can do is get the best indication of where that might be. We've been using things like our indicators to tell us titration's done, but different indicators change colors at different points. We can easily choose the wrong indicator and get a false point. Okay, and that becomes something we have to make sure we're using the right indicator. The titration errors, the difference in those, choosing the indicator, there are a lot of different ways to do it, and I'm not going to repeat all the stuff in the videos. We use things like KHP as a primary standard. We can go from, primary standard means you can go from mass to moles. That's the definition of a primary standard. So it's got to be something high purity, and you want it to be stable. Yes?
Don't indicators work over a specific range? So how are those accurate?
You have to choose the indicator to match where your change is going to be. So for the example, if we go back and talk about phenolphthalein, phenolphthalein goes from colorless at pH 7.5 to pink at about pH 9. And at pH 9, it's as dark pink as it's going to be. It's an ionization event. Loss of a proton causes a molecular rearrangement, the phenolphthalein molecule, and it goes from colorless to pink. So I choose that. If I'm doing an acid-base titration, neutral pH is, you start with an acid, it's acidic. I consume all that acid. As I add more base, it goes from acidic to neutral. Right above neutral, the color change starts to occur. And then as soon as I add just a little bit more, a couple hundredths of a mil, you've seen 1 drop will do you, all right, and those color changes, then it goes from the light pink to the dark pink. So as soon as it gets above pH 9, that ionization event is completely done. So you have to match where that curve is, where that color is, with your indicator. So we're going to learn in the upcoming chapters on pH titrations, there are hundreds of different choices. So even if you look at the hood today, above the hood, there's a color chart with, there's probably 50 or 60 different indicators on that. And each one of them changes a different color, and it also changes a different pH region. For example, the indicator we used last week in lab, it changed colors. It went from the, is it green yet? It went from the blue color to the yellow color down at pH 4. That one happened in the acidic region. But we were titrating the base with an acid to make a conjugate acid in the system. So you have to have personal knowledge, where is this endpoint going to be at, or the equivalence point going to be at, so that you match those up. And there's a huge, I mean, you can miss it by 50%. And we're going to talk about some of those errors as we go on. Okay, so establishing concentration, direct method, we'll do some of that. Standardization, we've been doing that with NaOH. Last couple of labs. Remember the dilution equation and to account for that in your calculations. I went over this example. So I've got a couple of others that are not in the notes. The thing I encourage you to do is to use the factor analysis. Volume and concentration equals moles. Use the stoichiometric relationship of the reaction, gets you to the moles of the reagent, and then you can get to volume of the reagent. Basically, you're solving CV equals CV. Concentration times volume equals moles. Goes a long way in solving these calculations. Just remember that relationship. So if you've got two of the other ones, you can always solve for the other one. So on this one, it wanted to know what was the volume of the NaOH. So to solve that, I needed to get how much moles of HCl were there and relate that to the moles of NaOH, and then finally solve the CV equals moles equation to find out what volume was. And I tell, looking at this just off the top of my head, that if I'm looking for volume and if I want to rearrange that, it's just a mental check that I try to do. If I'm looking for volume, volume is equal to moles divided by the concentration. So my final step, I should be dividing by concentration. That's exactly what I'm doing here. Okay, it just, to see something like that tells me I've probably got this set up right. And then the ultimate check to make sure that you're right is do the dimensional analysis and see all these units cancel out. Moles of HCl cancel out, liters cancel out, moles of NaOH cancel out. I'm left with liters of the compound that I'm looking for. That's my check. If I don't have what I'm looking for left on top, I don't have it set up right. So I encourage you to use dimensional analysis in your problems. This was another one that I did, similar type thing, but I worked through this one on the video. Grams of material cancel out, moles of the sodium oxalate cancel out, moles of sodium oxalate cancel out in the stoichiometry. Here we're trying to establish the concentration of the potassium permanganate. So if I want concentration, I need to have moles per liter. If I want molarity, I've got moles per liter. I've got the units I want. Okay. Set it up. We're doing the conversion where we went from grams of material to moles of material, then use the stoichiometric relationship between the two reagents, and then finally added the volume to it to find out what were the moles per liter. Okay, that was done in the video, so I want to do things that are not in the videos. So I'm giving you one to start with. You've done this 3 times in lab. This is standardization of KHP. I want you to demonstrate to me you understand how to do that calculation. So you got 25 mils of NaOH. Use that to titrate a certain mass of KHP. Gave you its formula weight, and I want to know what is the concentration of the NaOH. You've been doing your own labs. You should go do this when you're asleep.
The number mass.
Say again.
Can I have the mass? Can I see the
Okay. So the mass that we're titrating is 0.7864. So 0.7864 is the mass of KHP, and the molar mass is 204.22. And it's the 25 mil volume of it. Now, if you need to walk up the screen, feel free to. And 7. All 12 of you here. Four more. Last one. Okay, all in, fingers crossed. Oh my. Okay, some of you need to go back and look at your labs and see how you're doing that calculation. So, with that many of us missing that, I'm going to quickly go over this. I wasn't planning on doing this, but I think we need to. So start with what you know. You've got a certain mass of KHP. Go from grams to moles. So 204.22 grams of KHP for a mole of KHP. The stoichiometric relationship is 1 mole of KHP for 1 mole of NaOH. I'm looking for molarity. Okay, so I want to know what is the concentration of this in molarity. So that means I need moles of NaOH for a liter of solution. I've got moles. Now I just need to take and divide by the volume. It's 25 milliliters converted to liters. Need moles per liter. And when we do that, pretty sure that calculation is supposed to be out of it. So if you did choice C, I can see if you missed about one more decimal place, you didn't do the liters to milliliters conversion. but you missed it by 2 decimal places. I don't know how you missed it. Okay. I want you to understand those calculations that you're doing in the lab. But this is an example of what we do with the titration. We took a mass of a primary standard. We can weigh that out. We can go from mass to moles. Right? Then we can go our mole relationship to get moles of reagent divided by the volume, and we can calculate concentrations. Let me promise you, by the end of the semester, by lab final time, you need to know how to do that calculation. If you look at, I typically don't give the lab finals back, but I ask something very similar to this. I'll give you one of the calculations that we've done over the course of the semester, and I want you to duplicate that you understood what you did in the lab. So that's one of the things that you'll do in the prep for the lab final. Okay. Any questions on that? Do you not understand what it is? Simple mistakes? Okay. We live there sometimes. All right, here was another example that I did. This one, same type of information. We took volume and concentration of a reagent. In this case, it was the dichromate ion. Some of these things we may not be as familiar with. It reacts with iron, and takes the dichromate. This is a redox reaction, much like the reaction we're doing today, and converts it to chromium-3. Volume and concentration gives me the moles of titrant. From that, I can go from moles of the dichromate to moles of iron. So use the stoichiometric relationship, put in the molar mass. That gives me grams of iron. This one doesn't want molarity. It wants percent weight or percent mass. So then what I have to do is take the mass of the iron, divide by the mass of the sample, times 100 to get percent iron out of it. So we're getting a different type of information.
I'm sorry, are you going to make us balance a redox reaction?
So when we get to electrochemistry in chapter 18, you betcha. But right now, no. I'll give you a balanced reaction. What I consider is that I know, and depending on who you had Gen Chem under here, some of the faculty members never covered that chapter. So we're going to treat it as if we haven't ever balanced redox reactions before, but that's the end of the semester. Okay. I'm gonna teach you if you don't know already. If you do, you can help teach everybody else. So redox reactions are different, I'll tell you that. You have to not only, when we do traditional reactions, we balance them in terms of law of conservation of mass. The mass and number of atoms of reactants has to equal the number of atoms of the products. And as long as you do a atom inventory on each side, everything's happy. Redox reactions are different because the number of electrons lost has to equal the number of electrons gained. And that is a wrench in the balancing process. I mean, it's the potential problem that you have to deal with. And we'll talk about the strategy, how you do this. Okay, so I want to do a couple. So here's a reaction. So this is somewhat like we did in the lab last week. So if you haven't done your calculations, this will show you example of how to do those. Calcium carbonate reacts with nitric acid in a 1:2 ratio to produce calcium nitrate, CO2, and water. How many milliliters of a certain concentration of nitric acid are required to react with a certain mass of calcium carbonate? Substitute sodium carbonate in our standardization reaction that we did. So maybe this is good practice for you. So I start with what I know. And what I know is the mass of the primary standard that I have. So I've got 0.9857 grams of calcium carbonate. All right, the molar mass of calcium carbonate is 100.087 grams of calcium carbonate per mole of calcium carbonate. All right. This step in the middle is kind of up to you. 1 mole of calcium carbonate has 1 mole of carbonate. If you want to leave that out and do direct, that's fine. Okay, if you see that, if you're uncertain, put it in there to show it. Then you have that 1 mole of carbonate reacts with 2 moles of H+. That's coming from the nitric acid. Now I've got moles of nitric acid. I'm looking for volume. So this is my CD equals moles situation. I'll rearrange that. Volume is going to equal to the moles divided by the concentration. I've got moles already. So if I looked at my units, what's canceled out? Everything but the moles. I've got moles of H+. So I've got the moles. What I simply need to do is divide by concentration. And I'm going to get the answer I want. It's going to be in liters. All right, so if I take and divide by the concentration, point moles of H+ per liter, that means liters go on top of solution. So that's the units of my moles now cancel out. I'm left with liters. It seems like a big number. Did anybody else get that? And usually we talk about things in milliliters. So let's say 194 milliliters. Okay, question on that. You did something or had to do something very similar for the standardization of your HCl solution. Now here's another example. This is an old test question. Okay, you got a 400 gram sample that assayed 96.4% sodium sulfate. Okay, it required a certain volume of barium chloride solution to titrate out all the barium according to the reaction below. And all the reaction tells me is my stoichiometry is 1:1. So what I want to do is use this for standardization, and I want to know what is the concentration of that barium chloride solution. Okay, so just thinking about strategy, I'm looking for concentration of barium chloride. So that's going to equal to the moles of barium chloride per liters of barium chloride. The liters I've got. What I need to do is find out how many moles are there. Okay, so the strategy I'm going to use is going to be based on the information that's given. Now I've got a 400 gram sample, or sorry, 0.4 gram sample that has some barium in it. But the sample assays 94 or 96.4 grams sodium sulfate. That means there's some impurity in there per 100 grams of sample. Okay, so that allows units of grams of sample to cancel out. So now I've got grams of sodium sulfate. Don't have that. So I've got my handy dandy table. Sodium sulfate weighs 142.04. 142.04 grams of sodium sulfate for 1 mole of sodium sulfate. Okay, now the relationship is that 1 mole of sodium sulfate has 1 mole of sulfate in it, because that's what reacts in the titration. And again, I'd say that's an optional step. If you see that's a 1-to-1 relationship, don't have to add that. Now I can go from moles of sulfate, and it's a 1-to-1 stoichiometry. the moles of barium. So now I've got moles of barium. Again, barium to barium chloride is a 1-to-1. 1 mole of barium 2 plus for 1 mole of barium chloride. And I would say that's optional for you if you want to add that step. Now I simply just need to divide by the volume of solution in liters. Make sure you've got it in liters. Just to follow my units. Grams and grams canceled out. That was grams of sodium sulfate, grams of sodium sulfate, moles of sodium sulfate, moles of sodium sulfate, moles of sulfate, moles of sulfate, moles of barium, moles of barium. We've got moles of barium chloride per liter of solution. That's the units I'm looking for to find the concentration. So whatever that comes out to. The trick on this one is realizing what this means. Okay, that's kind of the thing that you've got to put together on this one. But whenever you have something that's impure, I mean that's basically what we're undoing on the previous example with the ore that we looked at. Okay, we took and found out how something was. What the purity of something was. Now we say that we're starting with something that's impure, and we're using that in the assay. It's fine if we know it's the thing that when we do an analysis, we have to have an established concentration. It doesn't matter if it's a pure reagent, as long as we know what it is. Okay, so this gives me the ability to go from mass to moles, and that's what I need. Okay? If it's 100% pure, that's okay. But if it's not, as long as I know how to account for it, we're there. Anybody get a number for this?
6.58 times 10 to the negative 2.
6.58 times 10 to the minus 2? Okay. Let's do another one. As you can see, this was a test question. This would involve some dilutions. So just to make sure you follow through all the steps, you've got some sodium carbonate standard. You took a certain mass of it that's primary standard grade. That means it's pure. You put it into a 250 ml volumetric flask. Then you took and dissolved a sample and diluted to the mark. 25 mil is titrated. What's the concentration of HCl? Okay, so this step was throwing me. So all you're doing that first here is dissolving that sample in 100 mils of water so you can stir it up. Then you're diluting it to 250. Then you're taking 25 mils of it and analyzing it. Okay? So the reaction that's going to occur, since we covered this in the lab, I would expect for you to know what this is. So if it reacts, it's going to produce the sodium chloride plus the bicarbonate carbonic acid, which is going to decompose to water and CO2 ultimately, but in the short, it's carbonic acid. So that's our reaction stoichiometry we have to take into account. So what we did was we had a certain volume of this HCl solution. So we know its volume, okay? We want to know its number of moles so we can find out what is its concentration. That's what we're trying to find out. So we know the mass plus the volume of the sodium carbonate, therefore we can establish its concentration. We know what it is, or we can calculate it. So we're taking to find out everything we know to find out the one unknown in this system. All right, so start with what we know. We've got a certain mass. If you need to move closer today, come up here on the front. I mean, I can't write much larger and get it on the screen. I mean, I have no problem if you want to move around. Start with what we know, and then go ahead and put that in the volume of it. It's in 250 milliliters. I'm going to go ahead and convert that to liters. I would normally do that just in my head. Okay, so now I use the molar mass of sodium carbonate. So if I look up sodium carbonate's molar mass in my handy table, it's 105.99 or 105.99 grams of sodium carbonate. Per mole of sodium carbonate. Okay, there is 1 mole of sodium carbonate decomposes to make 1 mole of carbonate. 1 mole of carbonate reacts with 2 moles of H plus in the reaction. Okay, that takes us to moles. Now, the last thing I need to do is divide by the volume. So the liters of HCl solution. All right, I'll check my units right quick. I've got milliliters and milliliters cancel out. I've got grams and grams cancel out. I've got moles and moles cancel out. Liters and liters cancel out. I've got moles of HCl, liters of HCl. But if you look, I've got another liters left here. Okay? I got to get rid of that. And the way I get rid of it is I need to know how much of the HCl solution I used. So this is where if you didn't take that into account, you'd be off by a factor of 10, which would have been the dilution factors. Okay, so I need to take and multiply that by, I'll put it in the green color here to see it cancel out, the 25 milliliters which was 0.025 liters of solution. Now my liters of solution cancels out, and I'm left with moles of HCl per liters of HCl solution. That should give me my right number.
Dr. Smith, I'm not quite sure why the 250 milliliters is in the equation.
Because that's what I put the sample in. So if I want to
I thought it was just saying it was 250 milliliter volumetric glass.
It was, but that's what the total moles of that sample are dissolved in. And then once I made that standard up, I took 25 mils of it. And 25 mils of it's what reacted with the HCl solution. So we'll do that exactly in the lab over the course of the semester. We'll make up a primary standard. We can establish its concentration. If it's easier for you to separate this out and to find out what is the concentration in this 250. So if you wanted to find out this concentration in the 250 volumetric is X. Okay. And then realize you took 25 mils of it.
I got 0.10. Yeah.
And it's going to be lower. You took that and titrated that with the HCl. That's essentially what you're.
Then why does it say that we dissolved in 100?
Yeah, it's just,
That's like you said.
Okay, that's what tripped me when I read it.
It's just talking about the process of making it.
The process of making it up. So you dissolve it in approximately 100 mils to get it in solution, and then you dilute it down to the mark once you get it all dissolved.
Okay, so that's when the 250 comes into play.
Yes.
Okay.
Really,
Yeah.
it's not adding.
Okay, so diluting the mark means you're going.
It's just how it was worded.
That's correct.
Okay.
It's a wording that's a little odd.
So you just don't add a solid to a volume flask. They want you to get it dissolved first.
Well, if you add a solid to the volumetric flask and fill it to the mark, you can't shake it up and stir it.
Okay, so that's when
You can't put a stir rod in there because that messes your volume up. So you have to dissolve it before you fill it up to the mark. So typically you fill it half full or so you can swirl it. Okay, either that or you dissolve it into a beaker and then transfer quantitatively. So once it's fully dissolved, transfer it with the funnel into the volumetric flask, rinse it out with a wash bottle to make sure you got all the drinks. That's the process used. Okay, so what did you end up getting? 0.1?
0.1.
Okay, it's setting these relationships up. Question on this one before I go to the next one. All right, we will come back to that, but you don't have time to do it in a minute. Let me see what else we got. So you'll come back and do that one. Now what we're switching to is looking at a different type of analysis. This is a metal analysis, and I'm wanting to know, we're going to do, this is a precipitation titration. I've got a certain volume and concentration of silver nitrate, and you're mixing it with a certain volume and concentration of NaCl. So I'm simply wanting to find out how much silver is there. Sometimes we do these to find out how much of the chlorine's there, the non-metal. But these are basically metal, non-metal titrations, just like the solubility things we did. So here what I know on mine is I know the volume and concentration, that should be milliliters, missing there. I know volume and concentration of the chloride. I can relate that with stoichiometry. So I've got 65 milliliters of solution. It's 0.0011 moles of the chloride ion per liter. I'm going to show you the millis are going to fall out of this. I've got 1 mole of chloride per 1 mole of silver in the reaction. And if I put that in terms of the volume, sorry, this is not a what is the concentration. I didn't read it all. This is a precipitation titration. We'll have to come back to this one. Scratch everything I just did. Okay. Just kidding.
Could you go back to the last slide really quick? I was calculating something different for the
Okay.
last problem.
All right. So I'll come back and work that problem. So this guy.
I'm just making sure I got everything.
Sure. Let me stop the video from recording. I'll back up.